Let's continue with fluid metering. We saw already what's the general idea. Now let's verify the models. Now the most common type will be the Venturi tube or the Orifice plates, which actually you've been working before with the Bernoulli equation or the mechanical equation for fluids. You should be able to model both of them. Now let's talk about the Venturi tube. As the name implies, this is a tube or a piping system, and we have this, let's say, throat right here. So this is the Venturi application. The pressure drop is very gentle. As you can see, there is time and distance for the pressure to drop. And you can see here there is a difference on height. This implies there is less pressure due to the higher velocity and vice versa. Now, as you can see here, guys, you can relate the area and the diameter of area 1 with respect to area 2. Then we got this equation, the one which I was telling you about. There is no work, there is no gravity because we are assuming they are in the same height. Therefore, the only important factors are pressure, velocity of 0.1, and pressure and velocity of 0.2. After solving, and of course velocity, you obtain it via the relationship between areas, diameters, volumetric flow rate, and so on. You get this value right here. So the flow rate will be equal to the area, which typically is the one you get here, A2, the pressure drop divided by the density of the fluid, and the relationship between the area 2 and area 1. So of course, if you have a greater, smaller ratio, you will be changing that right here. Now the orifice plates, the basis is pretty similar. We have this piping system and we got this intersection right here. And you can change these little orifice plates here so you can identify the different diameters. So typically they will change on size. So here's the flow, and then as you can see, the area is the area of the tube, and now the area right here is the area of this little orifice. As you can see, there is not that much time for the pressure drop, so the pressure drop is drastic. So you will have fluid crashing into the orifice plate right here, and a little bit fluid going here. So the change in pressure is greater due to the drastic change in velocity. Velocity will go here and the flow will be slower here. There will be a pressure drop, which you usually account here with P1 and P2. And actually the model is pretty similar. We don't have work, we don't have friction, or at least we assume a coefficient. We don't have external work. Gravity is the same because the levels are the same. So we get pressure, velocity in 0.1, pressure and velocity in 0.2. Once again, we will work most likely with either diameters or areas. We work for it. CD is the coefficient of pressure drop. Each plate will have its unique value. And once again, what you are relating is the change in pressure with respect of the area. So this is the model. We're not going to work with exercises, but I just wanted to let you know those are the typical applications. You have one velocity, you have one pressure. Pressure is easier to measure than velocity. So you have another pressure right here, and eventually it goes back to the same point. So what you want to do is exploit this knowledge of the diameters here and here and the pressure drops.